So hello, I'm Mosé. I'm a research software engineer at UCL, and I will talk about using Julia on the former fastest supercomputer in the world, which was Fugaku. So this was a work that we did last year with together with Milan and Valentin. And so, what is first of all A64FX? So A64FX is a CPU. ARM CPU uses the ARM architecture. It has 48 cores, and it has native support for floating point 16 bits, which is something new in the HPC domain. And one very special feature of this CPU is that it has the scalable vector extension, which means that the vector extension is not fixed. The vector width is not fixed, but it can be variable. And this is chosen at runtime by the processor. And Fugaku was the first supercomputer to use this CPU, and it has been the #1 in the top 500 for a couple of years before Frontier was put online. And this is powered by 158,000 processors for a total of 7.6 million cores. And what sets Fugaku apart from the rest of the most of the other machines in the top 500 list is that it has no accelerators. It uses only CPUs. And if you want to know more about what I'm going to tell you about in this talk, you can read our paper just in time. It was written in 3 days. Yeah, so there will be more details, but let's see. So we did a performance and scalability analysis of Julia on Fugaku. So first of all, we tried to define a function, a level 1 plus operation, which is AX plus AXPY, which is a scalar times a vector plus another vector. And we compared this, the function written there in Julia, like couple of lines of code in total, basically, and the BLAST functions provided by the vendor and some other binary implementations that are available in the ecosystem. And for this, basically, we're using here this function in Julia, which lets you call BLAST functions in external libraries. But Julia has this feature, it's called a BLAST trampoline, where you can choose which BLAST library to use. So we can easily test different libraries in this way. So here is the first plot, depending on the number of elements, basically in the vector, on the vectors, we can see the speed of these operations, and the Julia line is the blue one. So higher is better, and you can see that it has the best peak performance, and for the rest is usually comparable, competitive with Fujitsu BLAST. Fujitsu is a vendor of A64FX, so it is competitive with the BLAST provided by the vendor. Yeah, and also Bliss is another high-performance BLAST library, and again, this is usually comparable, especially at the higher, larger number of elements. This is using single precision, so 32-bit floating point numbers. We did the same also for double precision with 64-bit. The plot looks pretty much the same. Again, Julia gets actually the best peak performance. In this case, actually, Fujitsu BLAST has the best performance for larger elements, but still very close to Julia as well. And then we also did the same experiment for half precision, but unfortunately we don't have the implementation of BLAST enough precision for any other libraries. Instead, in Julia we use the same function for everything. So this is again the performance. It looks pretty much the same as the previous plots, but the higher, larger vectors are not as flat as before. But anyway, so we don't have any reference for the others, so this is the best as you can get anyway. So shallow waters, I think it was mentioned already before. So it's a code by Milan for CFD. It's written in Julia. Most importantly, it's type agnostic. So this means that you can use whatever floating point numbers that you want, including half precision. And yeah, Milan ran this code on A64FX. I don't think it was Fugaku, so I think it was Isambard, right? Yeah, but yeah, it's another machine with the same CPU. And so he found that this provided a 4 times speed up compared to using double precision, which makes sense for a memory-bound problem because you can put 4 more numbers basically in your operations. And the qualitative results of using these is pretty much the same as floating point of double precision. I guess a caveat of using low precision is that you need to scale back your problem, like scale down your problem in order to be able to do all your operations in a meaningful dynamic range. So it's not that you can just do any operations in a single half precision. You have also video to show the comparison between, I think, double and single precision. No.
But it says double and half precision.
Yeah. This is better. No! Is it okay? Okay. So you can see the comparison between double precision and half precision, and qualitatively it's basically the same. Again, but you get 4 times the speed. Cool. Next one. Again, this is the comparison of the speed. I think. Sorry, I don't see the plot here. So higher is better, probably, yes. And the half precision is the red line, yes. Inside this one is single precision, and this is double precision. So, yeah. Another analysis that we did on Fugaku was comparing performance of MPI operations, just pure MPI, just communication without any computation going on. And this was done like this. He's like one kernel, MPI kernel looks like written in Julia. If you're familiar with MPI, writing in any language is pretty much the same. So MPI.jl is a package which we use for doing MPI communication in Julia. It has to deal with many different MPI libraries that exist in the world, which is very painful, but yeah, it works, and we can do some performance comparison. So this is possible because Fugaku, the RIKEN, the institute which runs Fugaku, provides the reference values of the MPI communications. So here I'm comparing the performance that I measured using MPI.jl with the results from the RIKEN benchmarks written in C. This is the time, so latency of the communication ping pong. You have 2 nodes and send one message and receive one message back. There is some small overhead for smaller messages, but for larger messages, it's pretty much comparable. And we have also the throughput, yes. So throughput is basically the inverse of the previous plot. And you can see that actually when you do MPI communication anyway, you want to use larger messages to get better throughput. And Julia is within, I think, less than 1% from the RIKEN C benchmarks. Other benchmarks using MPI already use, again, some small overhead for smaller messages, but then it is pretty much comparable. Yes, this is using 1,500 ranks on 384 nodes. Another command gather the. So this is fun because Julia looks like a lower latency. 1 minute. Okay. Looks like it has lower latency. I think there is a problem with caching here because we don't do in these benchmarks. We don't do cache avoidance. Instead, they do implement cache avoidance in the C benchmarks, and the cache size of A64FX is exactly 64 kilobytes. So my guess is that we are doing some weird caching here. I don't think this is real, that Julia is faster. Yeah, the last benchmark is memory bandwidth. This is done on Okami, which is another system, not Fugaku. Yeah, using this the XPY program. So Fugaku A64FX has 4 NUMA domains. So we are doing the same runs in using different numbers of NUMA domains. So 1, 2, 3, and 4. We expect perfect scaling. It's actually very good. Up to 2 domains, there is a small drop of performance for 3 and 4, but this is comparable, especially for 1 and 2, is comparable with similar benchmarks that have been done in C on the same CPU. So this is the conclusion for this work. So Julia is not especially optimized for A64FX, not at all, but get very good performance thanks to LLVM. Compilation latency on A64FX is very painful, because and this is especially bad for a JIT language like Julia. Julia 1.9 has caching of native code, which kind of reduces the pain, but pre-compilation takes even longer in 1.9. So there is this trade-off. There is one caveat, is that in MPI, custom reduction don't work on non-Intel architecture, so this needs someone to fix this. And Julia has a native support for half precision floating point numbers, and actually thanks to Gabriel, also on AVX 5100. And I think that's all. Thanks.
We have time for a couple of questions.
Hello, thanks for the presentation. Just a simple question. Did you perhaps measure, informally perhaps, energy consumption on the CPU?
So Fugaku, when you run a job on Fugaku, they do report memory consumption. I don't have a good reference with anything else. So I have some numbers, but I cannot tell you it's good or it's bad. So they do share in the statistics also what's the ideal memory energy usage for the job. And I think usually Julia is within the ideal memory energy usage. But again, I would have to do a similar workload on C++, for example, to say, oh, Julia is okay or not. I don't know.
I was asking actually comparing to x86, but thank you.
Well, ARM in general tends to be less energy angry.
We still have time for another question.
Thinking forward to, does this work? Yeah. Thinking forward to other ARM systems like Grasshopper, I guess this is good news that Julia seems to perform well on ARM.
Mm-hmm. Yeah, again, this is all thanks to LLVM. We did nothing special for this. So yes, the vendor support for LLVM is very important.
So I guess my question is practicalities is, are we going to get ARM64FX CI infrastructure for? We have to add to the stack of minis, Mac minis on the.
Given the time that it takes to compile.
Well, it's actually more serious. Like, actually, like, are there outside like these centers? Are there ways you can get access to 64, like, to these machines, like these boxes? Like, do cloud providers provide you instances or all these sorts of things as well?
That I don't know. Okay, good.
So AWS has Neoverse 3 that you can spin up. And if you personally want one, it might be the best thing to buy a Mac Mini and then install Linux on top of it.
But you don't have SVE. Because what's cool about A64FX is SVE. But MacBook has a half precision native support for half precision, which is very cool.